Okay. Hi guys. Today we're going to be talking about convolution and Fourier property, or Fourier property, what properties. Convolution is the combination of two or more signals. In other terms, it is an integral that expresses the amount of overlap of one function when it is shifted over another function to produce a new function or generate a new function. Convolution is the passing of a signal through a filter, where this filter helps us achieve the desired output. Convolution can be expressed as y of t equal to x of t convoluted with h of t. Which is also equal to the integral of negative infinity to infinity x of tau times by h of t minus tau d. That is the definition for convolution. We also use these filters all the time, such as in voice filters, communication systems, or even those who wear glasses experience convolution as the light is filtered by the glasses into our eyes. And today we'll be talking about the Fourier transform property of convolution, which is expressed as x1 of t convoluted with x2 of t. Either way with Fourier. X1 j omega times x2 of j omega. Where this is the time domain and this is the frequency domain. Fourier transformation of convolution comes into play when we are solving complex equations. A Fourier transform is going from the time domain to the Fourier domain, or to the frequency domain, whatever you want to call it. Which can also, more simple, be expressed as x of t Fourier transform into Fourier of x j omega, which is simple terms. Now, Ishan has prepared an example and some proof for you guys, and he will take over from here.
Okay, yeah. So the Fourier transform property convolution is a really important one, and so we would need the proof for that. I have a really detailed proof in the handouts you guys have been given, and I'm just gonna do a quick one over here. So we have the property that x1 of t convoluted with x2 of t. When we do a Fourier transform on that, we get x1 of t, x1 of j omega times x2 of j omega, which is basically saying that this convolution in the time domain becomes multiplication in the frequency domain. So using this property of convolution and the Fourier transform definition, we have Fourier transform of our given signal equal to infinity to infinity. We have another one of these, and x1 tau 2 minus 3 t dt. Now in this equation, only this term is being operated. Only this and this term are being operated by dt, and the tau term is with d tau. So we can pull that out right here. So we'll have x1 of tau outside, and then we can just rewrite it x2 t minus tau e j omega t dt. I didn't do anything at all over there, I just rearranged stuff. Now, from the property of time shifting, you can see that this whole thing becomes just x2 of j omega e to the negative j omega tau, right? So this is also in the handout, so it's easier for you guys to see. that becomes that, and then we are left with negative infinity to infinity x1 of tau. Then we have, I'm gonna rewrite a little bit, so we have j omega tau d tau, and then we have x2. That was from the time shifting property of this. Now this, once again, through the time shifting property becomes x1 of j omega, and then we have x2 of j omega. That is how convolution becomes multiplication in the time domain. Then for the example, we're gonna do one example together. I'm gonna do the more complex one with you guys, and then you guys can do one on your own. So this question is important for reasons I would suggest you guys pay attention. Right, so this is an equation you might see in an RLC circuit where this will be the inductor, this is the capacitor, and this would be the resistor. And what we need to find is the frequency, the impulse response, h of t, and to find that, what we can do is use the property that we already know, that if two signals are convoluted, then we do a Fourier transform on those, we get y of j omega. And rearrange a little, we can get h of j omega is equal to y of j omega over x of j omega. And then we can do a inverse Fourier transform on all that to get the impulse response. Now, in all of this, the only complex part is what is an inverse Fourier transform, which actually isn't that hard because all we do is we rearrange the equation and then we use the tables that is at the back of the handout to find out the answer. So we're gonna do that. We're gonna do a Fourier transform on this. We have x of j omega is equal to a second derivative becomes j omega squared, and then we have y of t, that's just y of j omega. First derivative becomes this j omega, and then we have y of j omega, and then we have 6y of j omega. Now from this, we know that h of j omega is equal to y of j omega over x of j omega, which is equal to 1 over j omega squared plus 5 j omega plus 6. Now, what you can do is factor out this term, which comes out to be 1 over j omega plus 3 and j omega plus 2. Now comes in the partial fraction decomposition part I was talking about, which is getting an equation like that. So we have 1 over j omega plus 3 j omega plus 2 into something like a over j omega plus 3 plus b over j omega plus 2. So this, if we can get this equation to that form, we have successfully done partial fraction decomposition. And in order to do that, you take this whole term and multiply it on that side. So you get a of j omega plus 2, then you get b of j omega plus 3, right? We have 1 here. In order to find a, we can set j omega to negative 3. So if j omega is negative 3, 1 equals a negative 3 plus 2, and j omega negative 2 will give us 1 equals b negative 2 plus 3. This means a is negative 1, b is negative 2. Then we can just say that this equation is negative 1 over j omega plus 3 plus 1 over j omega plus 2. Now, if you look at the last page of your handout again, this literally transforms into one negative e to the negative 3t u of t plus e to the negative 2t u of t. If you want, you can take out the u of t common, and then we have negative e to the negative 3t plus e to the negative 2t. And that is your impulse response.
Okay, so given what Sean has taught us now, we have prepared a small little question for you guys with two parts. One part you'll do now, one part you'll do at home for homework. Don't hate me. And I will show the question in just a moment. Okay. So x of t would be equal to dy of t over dt plus 2y of t. Now the question is, find y of t when x of t, I'll write it over here, when x of t is equal to e negative t, u t. So try to find y of t when x of t is equal to e negative t, u of t. I'll give you guys like 2 minutes to try to solve that. And anyone who's feeling bold to come up here and do it yourselves, it's simple. But yeah, give it a shot. Okay. Should we solve it? Okay. Expected outcome. All right, so I'll solve it for you guys then. So the first step into this is that we want to find the Fourier transform of x of t. So basically, take that little transform. It's just x of j omega, which would then equal 1 over 1 plus j omega. Now that we have this, we can move on to the main function, which we'll write as the line x of t equals y of t over t 2y plus t. Taking the Fourier transform of this, we would have x j omega equals j omega y with j omega inside parentheses plus 2y j omega. Now we'll move like one more step in the right direction, and we'll bring a y of j omega over the equal sign, putting the j omega in front of it. Then we can equal j omega to h j omega, which can also equal 1 over 2 plus j omega. So now once we hit this step, we basically have that and this. So we'll combine the two, which I can write, which will be nice. Y of t, y of j omega, sorry, which will equal to better words, I'll do like this actually first. J omega. Times J omega. Move this down. And then we just plug in what we got before. It would be 1 plus J omega times 1 over 2 plus J omega. And then we'll use partial fraction decomposition. Which will show us that it is minus 1 plus J omega. And then from this, we can just move one simple step forward, which is to do inverse Fourier transformation, which will give us the answer to the question, which is when y of t will equal e of negative t minus e of negative 2t u of t, which is the final answer of this question. Now for the homework, I'll write it up here, which will be part B. Will be same thing, find x of t. No. We have x of t equals dy of t over dt plus 2y of t. Find y of t when x of t would be equal to just u of t. And using the methods we showed you, it's not that difficult to solve. No.
That's all. Any
Yeah.
questions?
Yeah, just if everyone needs help on understanding anything that we just explained.